right, so in this talk, compilers are neat and surprisingly approachable. Building a small one is an eye-opener. It's also a little bit of a rite of passage. I highly recommend it. Could I see a show of hands now that we're doing a show of hands? How many people here have heard about Perl 6? All right. How many people have heard about Perl, the programming language? Plenty more. Good. Just curious. This is what we'll do today. I'll start with giving some necessary background to this whole I built my own language thing. This is me. I'm Mäsak. I'm not sure I'm recognizable in that picture, but this is basically how I would look in South Park. There's lots of things to say about my role at the company and sort of the languages I usually touch as a software developer. But for today, I thought this quote would be adequate. Sort of, this is something my boss told me the other day. Sort of, oh, this is Carl. He knows ones and zeros. And I was thinking about that, and that's actually quite high praise. Like when you learn computers and so on, there's basically two things to know. There's ones and there's zeros. So if I master that, I'm pretty well off. And the background is this. Back in 2003 and so, that's basically 2/5 of a lifetime ago for me, I got involved with the wrong people, or actually, to be more correct, exactly the right people for me. And that was the Perl 6 community. It was just forming at that time. Perl 6 as a language didn't exist. I was kind of curious about languages. I had done Java at university. I was looking at the scripting languages, Perl, Python, Ruby, you know. I was reading books and things online and so on. And I stumbled on something called the apocalypses. Now that sounds very ominous, but it's basically the first few documents outlining what Perl 6 the language would be. They were vastly wrong, it turned out, sort of about details of syntax and so on, but they were a sort of good first guess back in the early 2000s. And I found the vision of the language Perl 6 to be completely exhilarating, and like, I definitely want to code in that language. And keep in mind, there was no implementation, just these sort of bare bones documents about what that language would be. So Perl 6 sort of has come into being between then and now, has been implemented. And the vision back then was of a refreshing modern language. Of course, it starts out from Perl 5 and sort of tries to modernize that, put all the nicest, newest insights about language design into the language. But mostly also, and I went back recently to the apocalypses and I was reminded of this, it describes a mutable language. That is, if you don't like the language as it stands, you're very free to go on and extend it. Not just in trivial ways, but in very fundamental ways. You can add your own syntactic constructs, you can add your own semantics, the way the control flow works and so on. In these design documents, it's very clear that you meant to use the language like that. So it sort of becomes a community experiment. Sort of everyone gets in on taking the language to the point that they want. And the mechanism to do this is macros. And some of you may be familiar with macros from other languages, like there are C macros, and there are macros in Lisp, and they're actually quite different. The big difference is C macros, they work on text, and Lisp macros, they work on syntax trees. And it's kind of generally regarded to be a bit safer and more interesting to work on the syntax trees. So the mechanism here was definitely the Lisp macros. Now it turns out you can do both in Perl 6. But this was the interesting part, that you can take your program and work on it at the syntax level and get entirely new things. And so back in 2003, I got involved with the Perl 6 design effort because I sort of wanted to see this language spring forth. I have some modest achievements that I can brag about, sort of influencing the design of the language. Here you see, for example, an implementation of Fibonacci. I think you can read it right off because it's quite similar to the mathematical definition. Like Fibonacci of 0 is 0, Fibonacci of 1 is 1, and then comes the sort of formula that does all the rest. If you have a number n, then you do Fibonacci of the two previous ones and you add them together. Now, the thing I contributed here is the nice and short way to write 1 and 0 in those parameters. Usually you can just write a variable there, but I said, what if we can sort of, so 0 here stands for something like int $anonymous variable where that variable is equal to 0. So you don't have to write it the long way, you just write it sort of as a 0 here, because that's the only thing you can pass into that variant. And well, this is Perl 6. I'm going to skip many of the other explanations of Perl 6. But it's nice to have been involved sort of in some small way here. Later I also had a sort of big contribution in rewriting the entire temporal spec, which is the way Perl 6 handles date and time. At that point it had been rewritten sort of 2 or 3 times with very little success, but sort of my version eventually made it into the language and got implemented, so that feels nice too. And I realized, sort of being part of this, that a programming language is human-made. It's built to capture our thinking patterns, and it's not just sort of provided by the Olympian gods somewhere. Languages are not given to us. It's much more clear with programming language than with natural languages that this is something that we have built together in order to express code, in order to express behavior in computers. And that's, I don't think that's sort of commonly known, that this is so close to us, sort of. It's not someone else much smarter who have sort of designed and implemented all our languages, but it's sort of people like us. But also, and this is an insight that is still with me, we're not nearly done yet. There is so much to keep developing and evolving with our programming languages. Like, this is still the early 21st century. We haven't had programming language for all that long, and we're going to see so much more in terms of being better at abstracting and expressing things. So it's a journey that we can, you know, still jump on. This is a very interesting time where we can still be of some kind of influence and sort of steer that journey. Not just use the programming languages, but actually contribute back to them. However, I realized after a couple of years that a number of years had gone by with Perl 6, the language had sort of gradually come into existence and you could run it on your computer and it was great, but still no macros. No one had sort of picked up that part, even though it was such a central part of the original charter, of the original vision, to have macros and to make this a mutable language that you could sort of democratically extend, as it were. Now, in an open source project, things get done because volunteers sort of step up and sort of become a champion for it. And it was a sad fact that no one had done that for macros. I can sort of understand why. There's also the phrase sort of when someone keeps going on about a thing they want in the language, finally someone shouts, "Well volunteered," and that's sort of a statement like, if you want it so much, why don't you do it? So I realized I had to do it. I sort of had to put on that sort of volunteer cap and go implement macros in Perl 6. So I applied for a grant to do that because I realized it would not be a small task. I started working on it. This is several years ago already. I actually got about halfway, which was nice because the halfway point got me paid out half of the grant money. And then I found a bunch of conceptual problems in sort of my initial description of macros. This is the technical term for getting stuck. And I realized eventually that I need to experiment in a faster medium. I can't just sit here and sort of experiment by trying to implement this in the Perl 6 engine itself. I need a separate sort of working laboratory where I can get macros working and then sort of port it back into Perl 6 when I finished that. So a new language was born, and this is the sort of cause of 007. Now, there's something missing in this picture. This is not the sort of logotype that you're familiar with, so I went ahead and added the... Now, it's actually the emoji is turned the other way, so I had to sort of turn it right with CSS. This is completely for, you know, what's it called, copyright protection measures and so on. No one can claim that I actually stole the 007 logo here. Instead of going through sort of boring language features one by one, I'm just going to show you some 007 code. And because this is a fairly sort of syntax-wise mundane language, I expect you to be able to just follow along and read it, because it's basically a hybrid on the syntax level between Perl 6 and Python and some JavaScript. So let's do 99 bottles of beer and sort of do our first 007 program here. So the goal is to sort of do all the 99 verses, right, and count down from 99 to 1. First, we need a small plural function. This one just takes a thing here, which is a word, and it conditionally adds an s to it if we had any number besides 1. So beer turns into beers in all the cases except when the number is 1. You see a couple of things here. The if statements don't need parentheses. I find that kind of nice. A little bit less cluttered. Of course, you can add them if you really want to, but they don't do anything. The reason you can have parentheses is that you have to have the braces for the blocks in the if statements. Otherwise, that wouldn't work. But I kind of like that too. I like forcing the blocks there. And you also see the concatenation operator between strings here. So no plus. Plus is only for addition. This is stolen directly from Perl, though with a different operator than in Perl 5, the same one as in Perl 6. Okay, so now we have plural. Now we can use that function to implement verse. And verse starts printing things. So given a number here, it prints the 4 rows of each verse here. So it starts with 99 bottles of beer on the wall, and then it continues down. And here you see we've consumed 1 bottle, so it doesn't do n plus 1 anymore, it just does n. And so we go on. We need to call this verse in a loop, which we do here. That's a for loop. It creates sort of a range, but that's actually an array. All the numbers from 0 up to 99 excluding, so 98 is the highest. Reverses that range, or reverses that array, and just loops through all the numbers. And it passes in beer count here to that verse function that we saw. And in all cases except the last one, it prints an empty line also. Oh, yeah, the say function is what you use for printing. I could have gone with print like in Python, but say as in Perl is kind of smaller and cuter. And you use this function a lot, so why not? All right. By the way, if you have any questions during the talk, I might address them during the talk if I feel we have time for it. I'm a little bit pressed with time on the slides, and I see I already used up a quarter of my time. So with your permission, I will gladly handle questions, most questions in the QA. But if you feel you have something pressing that probably everyone needs to know on the spot, then feel free to ask as well. Let's just do another example to show something that is not common for all languages. You can actually define your own custom operators. This is also taken from Perl 6. And defining a custom operator is quite easy. You just define a function and you give it a special name. So you say this is going to be a postfix operator. So you do a postfix colon, and then possibly within these angle brackets, you give the syntax, the sort of actual name of the operator. So this is postfix exclamation mark. It starts with the product of 1, and then it loops up from 2 to the number n that we had here, and just keeps multiplying everything. I don't have sort of fancy things in the language like star equals for multiplying something with itself, like most languages do, but hold on, you'll see how we will add them later. And same thing with n equals n plus 1, that's sort of the long way of writing n plus plus, right? And the idea is that we later with macros will be able to add all of that. Anyway, now that you've defined this postfix exclamation mark, you can go on ahead and use it in your program immediately. Sort of no extra step needed. This is how you define an operator. So just to be clear, all these 4 lines here, in standard 007, sort of when you load it from scratch, they won't even parse, won't even compile. But after you define this in your function, you can now parse this, and sort of your language has changed a little bit. You now have this extra operator that you didn't have just a moment ago. So the distinguishing feature of 007 is actually macros that we haven't seen yet. You define them kind of like functions, but I've saved off describing them until in a little bit. First, we'll need to make a detour about compilers in general. This phrase here, rich programmer food, is from a blog post back in 2007, as you see, written by someone called Steve Yege. And the blog post is actually quite influential. I know more people than me who have taken this blog post and been inspired by it, and basically started realizing that, hey, this compiler thing, it's actually A, quite fundamental, and B, not all that sort of insurmountable. You can actually approach it and do something with it, even if you are a sort of non-expert. Even if you're kind of an amateur, you can still get something out of it. So that's the entire thesis of the blog post. By building a compiler, you will finally understand computers. Like the compiler course has all the necessary ingredients of finally understanding and appreciating what computers do, sort of at depth. And as developers, we kind of want that, don't we? That doesn't sound so bad. This is a syntax tree. I'm sure most people have seen it at some point. It's also called an AST. The A stands for abstract. I was wondering for a long time, why is it called abstract syntax tree? What does abstract have to do with it? Well, it turns out abstract here simply means that we've removed some unnecessary details, things that might be part of the syntax, but that are not really necessary for describing the program. So we're sort of taking one step away from the actual program and the concrete way it looks, and we're looking at just keeping the details that we need to sort of talk abstractly about the program, which means that some different ways of writing a program, they might mean the same, so they might be inessential differences, and we might get the same AST for both of those. Like if you put different amounts of white space, that doesn't matter at all. So that might matter for a concrete syntax tree, but definitely not for an abstract syntax tree. When you're a compiler, you kind of look like this. So you take text as input, that's your source code, that's what we all write like, and it goes into the compiler, and basically the first job of the compiler is to take that source code and understand it. And understanding it means to create this abstract syntax tree, this AST here, because the compiler, the parser, needs to sort of figure out the structure, what fits into what, what's nested into what, into this compiler. And also, when it comes down to it, text as a flat format is a horrible format to actually go in and try to figure out and manipulate. So what the parsing essentially does here is to figure out all the structure that's already in your text, but that's not apparent in the text. So parsing is sort of lifting all this nice, beautiful tree structure out of the text that you wrote. Many people know compilers because compilers complain a lot and give you error messages and so on. That's simply when it fails in some way to create the AST, of course, because it's that important to the compiler to see what you actually wrote. So if you wrote something non-syntactical, you won't get a well-formed AST and the compiler will complain. Now we can do a lot of interesting things in the middle here when we actually have the AST, but the final step will be to sort of go down to some textual format again, to generate some target code. Now the target code can be machine-specific assembly code, it can be bytecode, it can be some other instruction P code and so on. It doesn't matter so much, but the main commonality is that it's also basically flat again. So we go from flat to tree-shaped to flat again. And as much of the compiler as possible happens here in the middle where we have these nice tree structures. Sometimes we create other structures as well. We can create call graphs and sort of graphs of basic blocks that show the different relations within the program, but the AST is pretty central to this. And you could call this a really high-level overview of a compiler. By the way, if you're an interpreter, you just skip the last step and you say, okay, I'm going to parse this to an AST, and then when I have the AST, I'm just going to run right off that. I'm not going to bother being efficient here and producing sort of machine-efficient code. I'm just going to basically climb around this tree like a spider and get the meaning out of that. So you sort of skip the last step. Now 007, it turns out, is an interpreter. That's kind of a choice you make. I'm sort of working on rewriting it as a compiler as well when it would generate the bytecode, but so far in its development, sort of in the first 4 years, I haven't had a pressing need to make it fast. So to the question if 007 is blazing fast yet, the answer is unfortunately no, but sort of it's in the works. So don't expect miracles if you actually go and run it. By the way, why the name 007? It's basically just a really poor play on words, where the internal data type inside of the language, which you'll encounter in some slides, for the AST is called Q. So all the AST types, all the types of nodes that you can have inside of your AST, they are called Q and something. Let's talk a little bit about these 3 parts here, the parser and the middle end and the code generator. So the parser takes your source text like we saw and builds an AST. You basically have sort of two jobs here at two different scales. The first one is sort of the top level one. Your entire program at its highest level contains of big chunks of statements, you know, if statements, while loops, and so on. Some of these have blocks which contain other statements, but it's sort of, when you parse top down, that's what you start to see. Sort of an entire program which is a stretch of, it's a statement list, and that statement list breaks down into statements and so on. And parsing this is actually quite straightforward, at least with the simplest methods. And one of the simplest one is recursive descent, which just goes through the program and its functions calling other functions. I'm not going to go into it in detail, but here you have, for example, for parsing a JSON array inside of the JSON language, you expect to always find an opening square bracket first, and then you might sort of take this track here and find a closing square bracket immediately, which is if you have an empty array, of course. Or you might have one value, which you take this middle way here, or you might have several values, but then you have to go around here, and for each new value that I expect, you need to parse a comma first. So this sort of captures all the three cases of an array that you might have, sort of 0 values, 1 value, and multiple values. And if we would were to express that in, let's say, JavaScript code, it will look something like this. This is basically the same trail chart that you saw on the previous diagram, but just expressed in terms of if statements up here, while statements, and a little bit of convenience methods here. The next opening bracket sort of means we expect to see an opening bracket here, and if we don't, we will fail. Whereas white here says it's allowed to have white space here. If you see any white space, just parse past that because we're not really interested in it. And then at some points we parse the closing bracket for the empty case, or the closing bracket for the one or more case. And here, down here is where we parse the comma. And if we ever find anything we don't expect, we just error out with bad array. Now, some of the logic here is just hidden behind these functions that we didn't see defined, but really not much actually. So recursive descent is exactly this, having just functions call functions, and by that you can build an entire parser. Doing the same thing in Perl 6 is a little bit nicer with nicer syntax. It's still the same technique happening, but now we express it in some sort of extended regex syntax. So the same thing that we saw here is this role array here. We say just surrounded by angle brackets. This tilde symbol here means surrounded by, and there should be an array list here, which is defined down here, which is 0 or more values. The star means 0 more, separated by commas. So it's kind of nicer and easier to express, but it's still the same code in the end. We could have written this out as if statements and while loops. Perl 6 makes it really easy to express grammars like this, and it's one of the reasons I've had an easy time writing the parser for 007, because I can just put things in this grammar way. An example actually from the 007 grammar written in Perl 6 is this one. If we want to parse an if statement, we do this. If optional whitespace, an X block, which is an expression and a block. So that's the sort of usual if statement. First you parse an expression. Remember, we don't need it in a parentheses. And then we parse a block, and we're done. Unless, and this whole part here is optional because there's a question mark here, we find some whitespace and an else, then we're still in the running here. We're still parsing, and we can expect one of two things here. Either a pointer block, which is just a block with a parameter. So it can actually take in as a parameter the value of the expression up here in the if statement, even if it was false. Or we expect kind of an else if, and then we sort of recurse into this statement if and parse from the top again. So it can sort of nest into itself. And you see how nice and short this is. You don't have to appreciate exactly all parts of this syntax to see that this is kind of a brief, nice way to parse an if statement. And it really helps to have that kind of parser here. So for me, at least, Perl 6 is already doing nice things. But then we have, at another level, it's also quite common to need to parse expressions. It turns out that this recursive descent that we just talked about, it's fine for larger level stuff, but it turns out to be too slow and too sort of in the way to do just operators. So here we have another kind of parser that does this kind of parsing. And just to give a feeling about it, let's go through the smallest possible expression where operator precedence sort of kicks in. And it's this one. Now pretend you are the parser here, and you do this sort of token by token. So first you see the 1 here, and you say, fine, okay, I got a 1, I'm going to store that away somewhere on some sort of stack. And then you see the asterisk here, and you say, okay, that's an operator. I'm going to store that one away also for now. Eventually we'll want to build this tree here, but we don't have enough yet. Now when you see the 2, you actually have enough to start to build a tree fragment. Why? Well, we're going to build this one, but at this point, after just parsing the 2, we don't know that yet. And that's simply because after the 2, there might be some other operator which binds tighter than the multiplication. And there are such operators in 007, so that might actually happen. So it's holding enough here to start building the first subtree, but it has to hold off until it sees the next thing. So now it sees the plus, and it goes, oh, I know plus. Plus is actually looser than the star here. So then we can build the subtree that we wanted. So now it sort of built this part, and then it still keeps holding on to the plus, and then it sees the 3 here, and it says, okay, I'm going to put that one away. So now we are holding sort of 3 things. We're holding this tree fragment here, a sort of loose plus here, and a loose 3. And then it says, okay, that's it. The expression is over. Okay, how am I going to sort of combine these last things? Well, I see I'm going to build this tree fragment with the plus and the 3. And so it does that. Keep in mind that in 007 you can also define your own custom operators, and they can play along nicely, set their own precedence and associativity and so on. So they need to sort of, if you are this parser, you also need to be able to react to new operators and to keep those in mind. That was a fun part to write, but surprisingly that wasn't that was one of the first parts that fell into place sort of within a year of the project. I would happily do that one again instead of having to implement macros, actually. Now the middle part, that's when you have an AST and you plan to keep it around as long as that's useful. So the middle part does various things, but mainly optimizing your program. It turns out that a lot of fun things happen inside of our compilers that we're not necessarily aware of. Like, it takes your entire program and rewrites it to a different program that does the same thing, except faster and more efficiently. And compilers are really, really good at this. I'm going to give you 2 examples, which will actually get us quite far in appreciating how it does this. So the first one is just constant propagation. Sometimes you're lucky in parsing through the program and getting this AST, and you can see things before even running the program, like how this will turn out. So here's an example. In our program, we've defined a constant. This is how you do it. Set my debug flag to true. It will never change because it has this constant annotation. And then later in the program, we do if debug flag. And you can see how you would totally do this in a program. You have a debug flag that you can turn on and off with different compilations. Now, we can see, if we are the compiler here and we sort of parse through this and we have the AST, we can see that this if statement will always be true. This if statement is unnecessary in the sense that we can just throw it away and replace it with the inside parts here. Do you agree with that? So let's do that. The compiler does that sort of fearlessly because it sees from the not yet run program that that's what always will happen. Now it has a better program that does the same thing, so no one will complain. So the rules of the game are completely disrespect what the user actually wrote, make up your own mind about what they meant, and write that instead. In Perl 6 land we say everything is fine if you don't get caught, sort of as the compiler. All manner of cheating as long as it's not visible on the outside. And so we remove it. Yeah. And we also remove the flag here because the flag now does nothing. If we see that we are declaring a variable and then never using it, it has no side effect or no anything. So we just remove that code as well. And again, the compiler is free to do this. It sees an unused variable somewhere. It knows everyone is going to be happy if it spits out bytecode that doesn't have that variable. Another example, inlining, and this is more of the same, but it's sort of in a different dimension. Here we have this verse function. Now we see it makes 3 calls to plural here, and those calls are going to cost something at runtime. They will cost something because we have to manage a call stack. We have to actually bind arguments to parameters and so on. Basically have to go to another part in the program. All these things are taking a little bit sort of minute parts of our time, and that's sort of wasteful. So what we can do instead is just inside this AST, copy paste the entire definition of the plural function into this one. And I'm not showing you the code here because it would be messy. But basically doing that in a safe way that copies in exactly the right needed code there. And you see we can, instead of binding parameters and so on, we can just put exactly the code that is needed there. So those upper ones would have n+1 in it, just inlined, and those lower ones would have n in it and so on. If we do that sort of with the proper respect for variables, we will have identical code, but without the function calls, which is much nicer. And we can go on with this. Now we have verse, which is just one piece of uninterrupted code that is just calling say a bunch of times. So we can take that one and put into the main loop here. Now we have no functions left in our program. We can go on with that as well and say, okay, this loop has a constant array that we're basically looping over. I can take that array and just unroll it during compilation. So I see all the sort of 99 iterations of this loop inside my AST. And then when we've done the loop unrolling, we can do aggressive constant propagation on that as well. So in the end, we just have a bunch of say statements. That's the entire program. And if you're wondering, well, wait, will compilers actually do that to my program? Yes, very yes. They will be that brash, and they are right to do so. So it's a fun realization, actually. The things we care about in our programs with, don't repeat yourself and sort of single source of truth and modularization and everything, the compiler comes in and smashes that, just destroys all that and says, we have a better idea here. We're going to duplicate your code everywhere so that it's faster. We sacrifice a lot of the program size for the speed, so it can be larger on disk if it's just faster and it gets rid of all these function calls and so on. And then we just optimize aggressively everything else. So repetition is bad for developers when we write the code, but it's sort of good for processors to have this code just spread out instead and sort of repeated all over the place. Now the code generator, I'm not going to talk about so much. It just takes the AST and flattens it as target code. Whereas I would say that parsing is kind of interesting and you're trying to extract information. It involves a lot of guessing. Code generation is fairly straightforward. You just run through the AST and spit out the instructions. It's a little bit more interesting than that, partly because you only have a finite amount of registers, for example, on a real machine. So you need to sort of decide which things goes into registers and which things spill over and so on. But basically that. It's downhill to a lower energy level. There's the alarm, yes. Thank you very much. Now I'm not saying we're completely done here. There are optimizations you can do also when you get the generated bytecode. For example, with just-in-time compilation, which is sort of state-of-the-art being done in our JavaScript engines and so on. That also we will skip today. Let's talk a little bit about the ladder of abstraction, sort of the tools we have in our toolkit when building languages to abstract code and make it cleaner and better to simply avoid these duplications. So this is the kind of thing that the compiler will come and destroy later. We have variables. Everyone knows about variables. They are used either sort of to define constants like this or something that we expect to change later. In 007, we write both of them with my. That's from Perl 6 as well, or Perl 5 or Perl 6. And we can mark things up as constants. That's done with that annotation. Moving on, functions are very important. They are ways to sort of only write things once in a program. It's useful in itself for ourselves and others to name the function well. We can also give it parameters so you can run it in different ways and so on. None of this, I expect, is very new to people. Here's a Quicksort implementation just to give an example of that. This happens to be a recursive function, so as part of the Quicksort is actually doing several recursive calls here. This works in 007 today without a problem. Yeah, we can use functions to do that. Also in 007, operators are functions as well. So even they help us soak up complexity. If you feel you're missing an operator in the language, you just define it as a function, or as we'll see later, as a macro, and that helps sort of with the complexity. So my take, you can always abstract things away with functions. Functions are actually really powerful here, especially when we have the closure functionality and so on. The one thing you don't get always is this extreme syntactic nicety. You might have to be content with a lot of function calls in your code, and it looks kind of messy and confusing and so on. But there's a lot of power in there, sort of a lot of expressive power that you get from just this level, from just functions. Then we have an important level as well, one that I didn't actually appreciate so much before I started with 007, but it's modules, to sort of getting away from a global namespace and also having separate parts of your program that communicate through known channels, sort of with an import-export mechanism and so on. That's also a huge part nowadays of getting your program structure to be manageable and understandable. It kind of got me into modular programming, actually. It was a big thing back in the 1960s and 70s, and I hadn't really seen how important modular programming was back then. It was sort of the next big step after structured programming, with, you know, if statements and while loops. Then they sort of came up on this one, and then at some point modular programming sort of got steamrolled over by object orientation. So that's all people talk about nowadays. Object orientation gets a lot of the credit for what modular programming once offered. It's sort of been baked into that. If you want to look further, Modular 2 is largely forgotten, but when you read through the language, it's actually, you can see that it's been a big influence for Python, for example. So one of sort of the dead ends of programming history, but still leaves a mark in what we use today. Then, of course, we have classes and objects. This is sort of on the forefront of what we're working on in 007 today. Here's a taste of it. I'm not super sure about the syntax yet, but that should also be fairly readable, right? We can declare our fields here. We have a constructor, we have a method. And in both the constructor and the method, magically just the self symbol is available, and you can refer to the object that you're in, sort of. This is behind the feature flag in 007. It's not so far evolved yet. You can define classes, but you can't do very much with them. My take on objects is actually they are nice, but not completely necessary. We can do a lot of decent things without them. Like if we just had modular programming, that would be super as well. So objects are an extra bonus on top of that. I like having an object system, but it would sort of make sense to do without it as well. I've started to think about this as the Eden of Scheme, sort of. Scheme had it mostly right, and sort of is a very modern language in that it gives us variables and functions and lexical scoping and closure, and you can get a lot of mileage out of that. By the way, I'm kind of annoyed that classes look the way they look. If they had been closer to functions, maybe we could have defined them like this instead. Like this is a class that you construct with red, green, and blue, and like all the code that you saw on the other slide can now just be summarized like this. You would define your method inside the class. So I'm kind of toying with the idea of defining classes like this instead, but we'll have a note later about trying not to be novel here, which is a big part of 007. Then we have interfaces as well. Interfaces give us a way to talk about objects implementing some behavior, but we're not talking about exactly how the behavior. So here's an iterator method and a has next and a next method. This is not implemented in 007 at all, but it is one possible way of abstracting things. Finally, we get to macros. And this is sort of, you want to take the language further, but the language itself kind of doesn't want to do that. You want to go beyond the language and define something on your own. Define some syntax on your own, or define some behavior of your own that doesn't fit into the language as it is. So 007 in itself is quite a small language, but it allows you to do this. So here we are finally. Most languages aren't growable beyond what was put into them from the start. Like they don't have this macro mechanism or something similar to just go on and define your own syntax or define your own other things. So my mission with 007 is kind of this, to as an experiment, try to put these syntactic Lisp macros into an algol-like language. And if you're wondering about algol here, it's just this big family of languages that we're all in nowadays. We're all sort of descendants of algol. So C and C++ and Java and JavaScript and C#, and Perl and even Python, they sort of all fall into this one. And they are mostly similar imperative languages as well. So let's talk about macros a little bit. And I see I have a couple of minutes left. A really quick intro to macros. You all know about template strings, I think. There are these strings here where you can put in interpolated expressions. So here we're putting in our variable name and title, and so the whole string here will be, hi, I'm James Bond, and I'm a secret agent with a license to kill. So basically, sort of your own building kit here, IKEA strings, like you take them and you build something out of them. Now, macros are that, but with code. So you have a macro here, take some parameters, and you spit out some code here. Quasi here means here comes a code object, like this AST that we talked about. And you have the option to actually take your macro argument here, which are also AST fragments, and place them into your code here in some way. So these funny triple braces things are a way to say splice in the AST here, just like we spliced in an interpolated expression into the string. So what are they all good for? Well, Syntactic Sugar for one. This one is an easy one to express. We can have a debug macro that only runs this if debug flag thing in if the debug flag is on. And I realize now I could have had the if expression outside. That would have been clearer. So either it generates the code or it doesn't generate it at all. That's the point. But with such a small macro, it's kind of unnecessary. Like we said, if your compiler is good anyway at constant propagation and just figuring out, will this code ever run? Like this if statement will always be true or always false. It will still do a good job at this. So that debug macro was one of my first examples of macro. But it's not a particularly strong example because of this. A good compiler will already do this for you. But this one, however, accessing information that's gone at runtime. So here we have a name macro. This is completely impossible to do with just functions, but you can do it with a macro. First, what the macro does, and then we'll see the definition. You have this small object here with some properties and so on. And if you pass that to name, if you pass your variable info here, the one defined up here, it will actually give you back the string info. It will print info here. And you can see that that cannot be done with just runtime information because the names of the variables, they are gone at runtime. If people are familiar with the C#, there's the name of operator that does this in C# as well. Similarly, you can get the names of properties here, foo and bas, they will also fall out here. And here's the small macro to do that. You take in an expression here, you check if it's a property. In that case, we just focus on the property. Then we check if what we have is an identifier, that is a variable. If it's not, then we say we can't handle this. We just bail out. And then we return a small AST here with just that identifier's name here. And this will be not exactly a string, but a small AST for a string. And that's exactly what we need to put back into the language for it to print the name. Nice, huh? By the way, this is our type checking operator with two tildes like this. So we're checking here if expression is of this type, and here you see an AST node type, and if it's not of that type. All right, another example of things we cannot do at runtime because it's sort of too late to do it. We have a built-in L value macro. And let me first describe the problem to you. You could call a macro with this kind of expression, increasing x by 1 inside of the macro. Now the danger of doing that is that inside of the macro someone accesses that expression several times, and out comes the wrong result because it sort of run this several times inside of the macro, and we never want that. So I made up something called the single evaluation rule. An AST fragment should only be interpolated once in a quasi to sort of respect this rule. Sort of we can only run something once inside of a macro, otherwise it runs too many times and it gets the wrong side effects, the wrong result. So what we actually want here is sort of the little box that the variable refers to where the value is stored. And there's simply no way to get that at runtime. It's the box is completely inaccessible to the programmer. But we can get it at compile time with the L value macro. So we say here, here's my variable, give me the box for it, and then we can do .read and .write on that box. And we've only evaluated the variable exactly once here inside of the L value macro. And then just in an object-oriented way, we refer to the box the rest of the way. Bypassing lexical rules, which we sometimes want. This is a swap function. It does exactly nothing because all it does is reorder the parameters that it got, but the parameters are copied values from the outside. So what we want is to actually access the things on the outside. We can't do that with a function, but we can do that with a macro, sort of take both boxes from them and then do some reading and writing between those. Again, here we respect the single evaluation rule. We can build new syntax, and this is of course a big part, but you can extend the language and sort of put in new parsing rules by doing this. So there's a parsed annotation, which you hook into the parser and tell it how it should understand the code and parse it. So here comes, for example, the assignment operators that we didn't have before. For example, star equals that we saw before. We expect an infix operator and then an equal sign, and this infix operator can be anything. It can be plus, it can be star, it can be sort of all of the other defined infix operators, and then we just take the box of that one and do a read and sort of build exactly the right AST here. You see we can put in operators as well and then write the result back. We can build new semantics. This one I kind of like. We can even define if statements inside of the language. Now, if statements are fairly low level, but just to give a taste of it, this is not something that's implemented, but something that I'm envisioning. We can generate bytecode for the if statement, which is the actual byte instructions would be something like jump in if falsy to this label that we've set up, and then we have the actual block for the if statement, and then we have the label here. So you can actually generate the right bytecode here, and that's how we can sort of, without getting into an infinite loop here, we can define if statements without actually needing to refer to if statements while defining them. We just talk about the bytecode that's generated. I'm going to, in the interest of time, skip past this example and just concluding here. The last part is language design hell, because while implementing a language is all fun and games, I'm such a klutz. Really, I can't believe how easily I fall for this, sort of putting myself into traps. The explicit goal of 007 is not to try to be novel. The experiment is trying to explore macros, not to sort of trying to explore new cool ways to language. And I'm doing this by just stealing from other languages, which is a fine way to do it. And yet, all the time, every little small choice I make as a language designer has repercussions somewhere. It's like a butterfly effect of badness. So not necessarily locally, not necessarily the same day or anything like that. It can be 6 months later I realize, oh no, this will not work. This is such a horrible idea. Like, bogus idea one. Let's make all the data types immutable because I like immutable value types. That sounded like a great idea. But the whole idea is about mutating the AST from within the code. So that will never work out. Okay, back to the drawing board with that one. So suddenly need to sort of implement a lot of mutating methods on arrays and so on. That was quite early in the language. Next sort of great idea was I can do construction of objects without using the new operator. Surely no one's thought of that before. So here's how you would sort of, it doesn't say new at the beginning. You just go ahead and create, sort of specify the type you want and then give a little block here with all the parameters. Kind of like you can do in C#, but without the new. Now that worked fine until I tried putting this in an if statement, sort of checking if this is of this type here, then, and this will get parsed as one of these constructor blocks and it will all blow up horribly. So now unfortunately I have the new operator. As an aside, I'm sort of thinking of rewriting this to the Python way of constructing things instead. Just call the type as a function and pass in the parameters instead. But that requires having named parameters, so I will sort of need to do that instead. Another tricky choice, and I went back and forth on this one a lot before I finally decided, this my declarator, should it be its own statement, which kind of makes sense, or should it be possible to put it inside of expression somewhere, which is kind of flexible and nice? Just to give you a sense of the difference, here you can do while my line equals read line and then compare it to none here, which you can do if it's a term, if it's part of an expression anywhere, which is nice. But it gets correspondingly harder to do exports of a variable if we want to do that with modules, or to mark a variable as constant, because suddenly my variables can sort of occur everywhere, not just at the top of the expression. So yeah, that seems to be a design choice without a right answer. Silly realization 4, writing documentation is super useful. Of course, I should have done this from the beginning. I started in earnest a couple of months ago. I realized so much along the way. Do write documentation. It's sort of excellent way to sort of therapeutic, and you realize a lot of things. But also, when you are designing a language, which I can't get away from the fact that I'm doing here, you can't avoid having an opinion. You can't avoid putting your opinion into the language, because how else will you do the language? You need to take these opinions from somewhere. And all your weaknesses, sort of as a language designer, will go into the language. And there's unfortunately no way around this, which is why I don't recommend the sort of activity of designing a language at all. Start with someone else's language instead. Implement that. There are just so many small realizations about how a language works under the hood, which by and large are good, but they're also painful to have. So, which is why implementing an existing language is a character building learning experience. Please do that. It's easier than you might think. You will have fun along the way, and suddenly you will have the power to actually write parsers and code generators and compilers, and that will serve you well in other activities. However, designing a language is kind of a death by 1,000 needles, so use extreme caution when you do that. And remember, we're not nearly done yet, so thank you. And I see that the pizza has arrived.